Imagine a giant library with every possible phrase from a book organized alphabetically. This is what a suffix tree is like for strings. A suffix tree is a special tree data structure. It stores all the suffixes of a given string in a compressed way. Think of it as a roadmap of the string, allowing us to navigate and search for patterns efficiently. Each path from the root to a leaf represents a suffix of the string. Each edge is labeled with a substring of the string. Let's take an example. Consider the string banana. Its suffixes are banana, anana, nana, ana, na, and a. A suffix tree for banana would have branches representing each of these suffixes. Internal nodes are often compressed to represent repeated patterns in these suffixes. Suffix trees are powerful tools for string processing. They allow us to solve many problems efficiently. These problems include pattern searching, finding the longest repeated substring, and more. Their compressed structure makes them memory efficient, even for large strings. Understanding suffix trees opens up a world of possibilities in string algorithms. The concept of a suffix tree was first introduced by Weiner in 1973. It was later improved by McCreight in 1976 and Ukkonen in 1995. These improvements made the construction of suffix trees more efficient. Suffix trees have become an essential data structure in computer science. They are used in various applications, such as bioinformatics, information retrieval, and data compression. Suffix trees are like Swiss Army knives for string processing. They offer elegant solutions to a wide range of problems. One of the most common applications is pattern searching. Given a text and a pattern, we can use a suffix tree to find all occurrences of the pattern in the text in linear time. This is much faster than naive pattern searching algorithms, which can take quadratic time or worse. Another important application is finding the longest repeated substring in a string. This has applications in DNA analysis, plagiarism detection, and data compression. Suffix trees can also be used to find the longest common substring between two strings. This has applications in bioinformatics, for example, in aligning DNA sequences. Suffix trees are also used in other areas, such as autocomplete systems, spell checkers, and data compression. In autocomplete systems, they can be used to suggest possible words based on the prefix typed by the user. In spell checkers, they can be used to find words in a dictionary that are similar to a misspelled word. In data compression, suffix trees can be used to find repeated patterns in a file, which can then be replaced with shorter codes to reduce the file size. The power of suffix trees lies in their ability to capture the structure of a string in a compact and efficient way. By traversing the tree, we can quickly extract information about the string, such as the frequency of a particular substring or the longest common prefix between two suffixes. This makes them an invaluable tool for anyone working with strings and text data. Building a suffix tree might seem daunting at first. However, with a step-by-step approach, it becomes easier to understand. We start by adding each suffix of the string into the tree, one by one. Each suffix is represented by a path from the root to a new leaf node. Let's illustrate this with our banana example. We begin with the suffix banana. We create a path from the root, adding edges for each character B, A, an, and A. Next, we add the suffix anana. Instead of adding all characters again, we find the longest common prefix with the existing tree. We reuse the existing path for A and branch out from there, adding nodes for N, A, N, and A. We repeat this process for all suffixes. The key is to maximize the reuse of existing paths. This ensures that the tree remains compact. Special characters, often denoted as $, are added to each suffix to mark the end. This prevents shorter suffixes from being treated as prefixes of longer ones. There are efficient algorithms like Ukkonen's algorithm that can construct a suffix tree in linear time. These algorithms cleverly reuse information from previously added suffixes to speed up the process. While the details of these algorithms are beyond the scope of this essay, understanding the basic building blocks is crucial for appreciating the elegance and efficiency of suffix trees. Once a suffix tree is built, searching for a pattern becomes a breeze. It's like having a detailed map and knowing exactly where to look. We start at the root of the tree and follow the path matching the characters of our pattern. For example, let's search for the pattern Anna in our banana suffix tree. Starting at the root, we follow the edge labeled A. Then we move to the child node and follow the edge labeled N. Finally, we follow the edge labeled A. Since we have successfully matched all characters of our pattern, we know that the pattern Anna exists in the string. The real magic happens when a path splits or doesn't have a matching character. If a path splits, it means the pattern occurs multiple times. We simply explore all branches below for each occurrence. If there's no matching character, the pattern doesn't exist in the string. The time complexity of searching for a pattern of length m in a string of length and is ohm using a suffix tree. This is independent of the size of the text. This makes suffix trees incredibly efficient for searching patterns in large texts, such as genomic sequences or large databases. They are a testament to the power of clever data structures in solving complex problems efficiently.